Today, I'm super excited to be joined by Anders Sandberg. Anders is a research fellow at Oxford University's Future of Humanity Institute, which is this amazing institute that is looking into really big picture questions of our time. Things like, what is our place in the universe and how can we best ensure a positive future for the human race? And Anders is known as an academic jack of all trades, and he certainly is one of the most polymaths I've ever met. He originally got his Ph.D. in computational neuroscience, but these days spends his time spearheading research on topics ranging from transhumanism, global catastrophic risk, emerging technologies, trying to resolve the Fermi paradox, and the technological considerations necessary for far future space exploration. Thanks so much for joining me, Anders. There are obviously countless topics that we could talk about today, but what I'd really like to focus on is your upcoming book, Grand Futures. Can you give me a little bit of an overview of what it's about?
So a lot of the research we do at the Future Humanity Institute deals with how things could go badly wrong, existential risks, ways we might lose out on all the future. Mm-hmm. And often people ask us, but how can you even sleep at night? What motivates you? And the real reason is, of course, we're pretty optimistic, because if we do survive and get our act together, which might be a slim chance, but it's still a chance, then the future looks potentially really good, really big. And I'm trying to quantify that. I'm actually trying to basically figure out how grand could the future be.
So what are the kind of the dimensions that you're trying to quantify?
So one of the most obvious ones is, of course, how far could we spread? If we go outside Earth, how far into space could we go? But another one is survival. How far into the future could we survive? And then, of course, how good could life be materially? Can we get hold of matter and energy to produce a really wealthy civilization that's also sustainable? And then there are interesting questions like, how much computation can we do? How much lives could there be? What are the limits on how good things could be in a moral or aesthetic or in some other philosophical sense?
So with the question how many lives there could be, I suppose the sort of parameters that you've got to look at, what is the energy availability that's required to sustain a life? So have you come to any numbers of an upper bound of how many lives could exist?
Yeah, but it all depends on what you mean by a life, of course. So this all began actually in the 1600s. Leeuwenhoek, the guy who invented the microscope, he also wrote a little essay about how many people could live on Earth. So based on modern agriculture in the 1600s in the Netherlands, he estimated about 10 to 13 billion people, which is not terribly weird.
Seems like we're going to plateau at around 11 billion.
Something like that. But people have been using this estimate henceforth in all sorts of ways. Typically you try to calculate the kind of agriculture you think makes sense, and then you calculate how many people can live on it. If you're a more doomy environmentalist, you say, well, our current ecosystem can't take it, you need smaller populations. And if you're a real techno-optimist, you might say, actually, screw the ecosystem. Let's plant soybeans across all the land surface and turn the oceans into algal farms, and now we can have 10 trillion people living in some arcology somewhere. So it all depends on how much nature you accept there.
Right.
But of course you could say, that's just one planet. Earth is relatively small. What if we went out and settled other places? So you can use this kind of reasoning, but you should always be careful about that future generation might not want to live like that. Mm-hmm. But certainly we could take the asteroid belt and turn that into a habitat that could house at least a few trillion people. That's already quite a lot of people. And of course that's going to last for a long time too. Because at least up until the point where the sun becomes a red giant in about 5.2 billion years, they are going to do pretty well. And of course, if you live in space habitats, maybe you move some of them to other solar systems. And in the Milky Way got 300 billion stars.
Right. And each one has roughly one planet.
At least one planet, probably more. And probably a lot of asteroids and other building material. So this already produces some astonishingly large numbers. You multiply kind of billions of people per planet or trillions of people per solar system with hundreds of billions of solar systems, and that's one galaxy. Right. And we can reach a few billion galaxies too.
A really common way of thinking about the different stages of possible civilizations that either we could have or an alien civilization that's suitably technologically advanced is the Kardashev scale. As I understand it, a Kardashev level 1 civilization We're not there yet, but we're sort of halfway there, right? Where basically the definition is that a civilization that has managed to harness the sort of energy potential of its home planet. That I can see how we could get to relatively easily, but stage 2 is where you manage to harness the energy of your local star. So how would a civilization go about doing that? How would we do that?
Well, we have already started in a sense. We have some satellites orbiting the sun with solar panels. It's just that's a very first small step. We could imagine adding more and more solar panels to space. And eventually you just cover the entire sun. You have an orbiting sphere of orbiting panels. This is called the Dyson Sphere after Freeman Dyson, a physicist who suggested that we should look for them as signs of advanced civilizations out in space.
And what would they look like?
Well, that's the fun thing, because you would probably just see this opaque sphere that would be picking up all the sunlight and turning it into useful work, but then eventually becomes, of course, waste heat. So it would have a temperature that basically averages out. So his calculations was that it was about Earth temperature, 300 Kelvin. But that's kind of arbitrary, but you would expect it to be an infrared source. And since this is not a solid shell, it's actually a swarm of orbiting things, you might see glints of sunlight through
right,
that. So,
like through the gaps.
Yeah. And if you want to keep a planet that you kind of like and cherish, maybe you can have the solar panels tilt straight towards the sun when they pass through. So you might have Earth orbiting outside the shell and getting all the sunlight. So you might have the opening sending off light.
Right, but at the same time, I can imagine you could really focus that light too.
Yeah, so of course you could play around with mirrors, but it's probably even more effective if you take these solar panels. And now you have, notice, 10 to the 26 watts of power, and maybe you use it to power a laser, for example.
And what would you do with a laser like that?
Well, of course, the ultimate version of a kid frying ants with a magnifying glass might be focusing that laser on some remote planet, which is not going to be good for the planet.
So interstellar warfare, basically.
You could do that, but it's actually surprisingly crappy for interstellar warfare, and which is probably very good news. Basically, you probably want to use that energy for more peaceful applications, but you can, of course, send signals over long distances, which is easy because you have a receiver that you know where they are. But if you want to kind of attack somebody, you also need to know where to focus that energy. So having an enormously large sphere with lasers on, you can focus actually very sharply, but you need to know where it is. So a planet is an easy target, but suppose now people are running away in a spaceship, randomly changing course. They're light years away. So you
tiny little thing in terms of,
And you can try sweeping around your laser, but space is big.
Yeah.
So this is actually pretty good news. And one thing I've been interested in the book is, are there physical limits to warfare? How much damage can you do? How much can you protect yourself against? And one of the nice pieces of news is that space is so big that it's actually very hard to do damage if you don't know where to aim damaging effects. In fact, most of our matter is probably pretty fragile if somebody knows where it is, but if you can hide really well in space. Now, you could of course imagine two Dyson spheres shooting lasers at each other, but again, they're intended to be good at picking up energy, and you might burn out a few of these panels. It's actually, again, fairly inefficient. So I would expect that advanced civilizations, if they want to go to war, they use some other means. What you really want the Dyson sphere for is, of course, to do computations, to run your computers, or maybe power your spacecraft because you can accelerate spacecraft, or just run your homes, whatever the homes are like.
How would you extract? So because we have this beautiful MOVA globe here that we can use. It's actually Venus, but let's assume it's the sun because it looks similar, right? So to explain for the viewers, you would harvest some kind of body that's close to the star. So in our case, Mercury, I guess, is the nearest body.
I'm kind of hungry for Mercury, but we might want to start with the asteroid belt too.
But the asteroid belt's so far away, you've got to get... I guess you can just use the gravity to pull it in quite easily. You don't have to do that much.
You have an interesting problem, though, because gravity doesn't just pull. An orbiting asteroid has a velocity that you need to get rid of for it to get close to the sun.
Right.
It's kind of ironic. The change in velocity you need to get close to the sun is quite much bigger than you need to get to the outer reaches of the solar system. But there is a nice thing you can do here. You
need to slow it down.
Yeah.
You need to negative.
But what you can do is you take that asteroid, you mine material from it, and in particular you mine a lot of aluminium or other metal and make a big solar sail. and then you use sunlight to slow it down. And now you don't need to waste any matter for a rocket exhaust. It takes a while because sunlight is a fairly weak force. But now you can spiral inwards and put them into place. But personally, if I want to quickly get a Dyson Sphere, I would take Mercury. I would put in some robots on the surface. They have solar panels. There's a lot of sunlight on Mercury. They mine the material. They make more solar panels, more robots, and keep on doing this. And it turns out that after a few decades, what started as a few robots, by now, of course, they cover the entire surface and are mining the upper layer all the time. At this point, it becomes very tricky, actually, both to cool down Mercury, because there's so much industry going on, and just the robots are getting in the way for each other. So there are some logistical problems that need to be solved. But basically, it takes about 40 years of exponential growth to totally disassemble Mercury.
And would Mercury provide enough, the materials, I don't know how thick each solar panel would be?
So that depends very much on what style of Dyson Sphere you want to have. So if we want the kind of normal thick solar panel, Mercury is a bit wussy. You might want some other planet. Venus might be in trouble. But you can also do things that are much lighter. So one elegant solution is to use really, really thin aluminium foil. If it's thin enough, the light pressure of the sun will exactly counterbalance gravity. So it will just hang there. It doesn't even orbit. Now, for that, you only need a biggish asteroid like Vesta. Now, that in itself is fairly useless except as a decoration. You get the ultimate Christmas bauble. But now you can use these panels. You tilt them slightly to focus sunlight onto some black body. That gets very hot. And then you connect that to something on the outside, a cooling element, and now you have a heat flow. A lot of heat flowing through. And this way you can get a lot of energy. In fact, you could do this out of iron and steam and do a steampunk Dyson Sphere.
Steampunk Dyson Sphere, that I can't picture, but I want to exist very much.
Yeah, it would be pretty awesome. And it might very well be that really advanced civilizations, once we did the first Dyson Spheres that we're dead serious about, and now we have extra resources, now we're starting to do the artistic ones, the funny ones, the hilarious
novelty ones, yeah.
Yeah, the meme Dyson Spheres.
Nice. So you have this sort of presumably close to spherical shell at some radius away from the sun. How do you extract that energy and get it somewhere meaningful? Like, do they have wires between them? What are you going to do?
So people have been interested in beaming power in space for a long while. So solar panels on Earth have this problem that it's actually night half of the time. Well, not if you go to sufficient far north and south, but still. Well, on average, it's still kind of night half of the time, even after the North Pole. But the idea would be, let's put them into orbit and then use microwaves to beam it down to receiver station. The little problem is that a lot of people say, wait a minute, microwave beams from space? Oh dear, that sounds rather scary.
Yeah.
So actually getting this to work is both technically hard. You lose a lot of conversions from the solar panel to the receiver, and you still need to convince the neighbors that this is a safe idea. So it seems tricky, but in the Dyson Sphere, this probably makes a lot of sense because now you don't have so many places to fry. You have deliberately built it up. You might want to use lasers or other systems too for more intense energy transmission. So it might be that you have a lot of space habitat among the solar panels, so you beam in energy to them. So you have either your solar panels producing electricity and sending things over, or you have these, maybe not steam engines, but you actually use thermal solar energy. And it might be that the panels themselves contain the civilization, because on the back side you have just computers. Because it's not entirely obvious that advanced civilization will want to stay flesh and blood.
Right.
It might very well be that many of them decide to become software and live as a kind of solid state civilization.
And then in which case you just want to optimize for computational power.
Yeah.
So in that situation, would a civilization even have a desire to then go on to the next step, which we haven't talked about, becoming a type 3 civilization, which has basically harnessed the power of the entire galaxy, so every single star.
Yeah, it's an interesting question because some people think that, oh, it's so obvious that we're all going to upload into computers and live inside these servers and play World of Warcraft or whatever until the end of time. And that explains why we're not seeing any aliens. The problem with that is it assumes that everybody really, really wants to do that. Not just every human, but every individual alien in every possible alien civilization. And as a sociological prediction, that's bold.
Yeah, right? There's a lot of value systems to assume that you know.
And it might be that the vast majority actually are very content to live inside their servers or do whatever they do. But it's enough that a tiny minority wants to go out there for things to happen. It's a bit like our current civilization. We're tremendously rich compared to our ancestors in the Neolithic. And while most of us are spending the resources in normal ways, some of us do weird art projects or innovation and do things that change the world. It's a tiny set. Most people are totally normal and mainstream, but those
edges. Yeah, I mean, there's still people who also choose to live in sort of 1700s technology. So
indeed, it's kind of a good backup to have them. Unless,
absolutely.
It might turn out that we're doing something very bad by going high tech. So we should have backups.
Yeah, you want that diversity of preference.
Yeah, indeed, that's an important thing when thinking about grand futures. When I start describing encapsulating stars into solar panels, a lot of people shudder. And I typically first think, I haven't even started yet. But they already feel that is horrifying. Disassembling planets is totally out. Because they don't want a grand future. They want a modest future. They envision having tea with the vicar while people are playing cricket on the village green in some nice, sensible village with reasonable social relations. I think that's a fairly common view, and I think we should totally make sure people can live lives like that. So that's why we might want to keep the Earth and make sure it gets sunlight, even if a lot of others go out and colonize the Dyson Sphere.
Right.
And similarly, with others who are not content to live virtually, they might want to go out there into the big dark and do other grand things.
Yeah. So the next step then, so let's say we've got to the stage where we've harnessed the majority of the sun's power, and we can use that to now extend out to local star systems and beyond. How would we go about that?
So if you're very patient, you can just send something using 1970s technology. The Voyager probes, if we had aimed them slightly differently, would have transported the Voyager probes and that plaque with music to another solar system. It's just that they're not aimed in anywhere particular, and it's not going to arrive there very functional. Maybe the plaque is going to be intact, but none of the computers and technology work. But in principle, if you are willing to spend a few tens or hundreds of thousands of years of transport, you can do it using very low-tech things. But if we assume we're a bit more impatient, you can use, of course, that energy from the Dyson Sphere to accelerate things to a much higher velocity. So I calculated together with my colleague Stuart Armstrong that you need about 6 hours of sunlight to send probes not just to all the stars in the Milky Way, but to all the reachable galaxies.
What? How?
Well, basically what you do is that you either use a coil gun, that is, you have electromagnetic coils and you magnetically accelerate a projectile. It's a bit similar to a railgun, but there you have an electrical connector, and since it's moving very fast, things get very hairy to actually get this to hold together. While talking about this, Eric Drexler, who was sitting next to me, pointed out, oh, kids today, they don't know how to build proper interstellar probes. He pointed out that lasers are probably even better. Right. If you have the right kind of laser, very finely tuned for the right kind of receiver crystal, then you can actually accelerate just using light pressure. And use a lot of power to accelerate.
On a solar sail. Well, sorry, not a light sail.
Yeah. And you can do it in various ways. So there is the Breakthrough Starshot initiative that actually aims at, within a few decades, send these small microchip-like probes to Proxima Centauri using a big laser. Now, if you have a Dyson Sphere, you can make bigger lasers. Much bigger lasers, but it might still just be a good idea to send very small probes, because when you're moving very fast, if you meet a big grain of dust, that collision is going to be oops.
Yeah, of course. And so what sort of fractions of light speed are we talking that you could get?
Yeah, so Breakthrough Starshot thinks that 20% is doable, which is ambitious given our current technology, but they're good people and they are thinking through engineering.
So you have to get you to Proxima Centauri in just over 20 years, right?
Yeah. Which is decent, but it's going to take a while to get to Andromeda this way.
Yes.
So I think you can definitely get up to at least 90 or even 99% of light speed. You need to do some interesting engineering. The problem is, of course, the dust issue becomes nastier and nastier the faster you go. Not only the dust, but also the gas in interstellar space. Normally we would say, oh, that's just hydrogen gas hanging around. But now it's going to appear like a proton beam hitting your spacecraft.
Head on.
Yeah. So you better have good self-repair, or you send a lot of small craft and don't mind that a few of them blow up during the way.
Okay, so this is all for sort of probes that we could send out to presumably gather information, send it back to us, and so on. But what about physically transporting biological matter? Is that even doable?
I don't know. I think it's going to be very tough. If you can build a Dyson Sphere, you can probably actually make a classic starship and send the biological people. But it's going to take a lot more resources. It's going to be one of those real ambitious things that are probably not that cost effective. Because the problem is, of course, moving very fast. Okay, now you have a lot of risk and you need a lot of shielding, and the radiation is not going to be good for biological people. No. And even then, you need an enormous amount of reaction mass to slow down at the destination. So personally, I think it's most likely the biological humans never leave the solar system. But we might be sending these small probes with enough nanotechnology to land on an asteroid, again, unfold the solar panels, a little bit of robots mining stuff and building more robot solar panels and turning that into industry. But then can maybe make a habitat, and then you actually artificially put together cells and create a little biosphere and put people in there. This, of course, presupposes that you have good enough nanotechnology to do this with a small seed probe. But we kind of have a demonstration already in form of acorns. An acorn is a little seed that can generate a multi-ton oak. It just takes a few decades or centuries and a lot of sunlight.
But how can you do that with a human?
Well, you could probably hide the human genetic material inside that. It's just that we don't have the biotechnology to make acorns that make humans, which is an interesting, mildly disturbing idea. But you could imagine nanotechnology doing the same thing. Yeah. If you can actually make things on a molecular level, it's no problem of actually putting all of the UK into... if you, according to some calculations I did, I think there is enough space to store the neural state of all people in the UK inside an acorn-sized computer. This is still presupposes a pretty advanced form of nanotechnology, but we have plenty of time to develop that. And of course, you need those robot nannies, etc., to actually rear people.
Right, exactly. Give them an environment to.
So it's going to require a fairly high technological level. It's harder to analyze this than solar collectors, but I think one can make a pretty strong case that this is physically possible, because we see a lot of very similar processes, and one can then delve into what do we need to build and discover.
So, let's say we can get to the stage, we could send a probe out to neighbouring star systems that can plant a seed of life that then grows a new colony there. How long could it take to sort of spread across the entire Milky Way? Are there just gaps that are too big to, because our locals, our nearest neighbour is 4 light years away, but presumably some of those gaps are much larger, right?
Yeah, so that's a very interesting issue, because it might be that it's not that much dust and we can make very resilient space probes, in which case we can just go all the way. The time it takes is just going to depend on how fast we can go. But it's not implausible that at least inside the galaxy there is too much dust, at least if you try to move along the disk. If you look up at the Milky Way in a really good place, you can see these dark dust lanes. That is because all the light from the stars on the other side hit a dust particle. Most of that absorption is by tiny ones that probably don't disturb the probes, but embedded in that there might be more dangerous ones. So it might be that you can't go that far before hitting something, which means that you need to move over shorter distances. Now, if we could only travel, let's say, 1 light year, we would be stuck here. Right. We couldn't get over to Proxima Centauri. If we could move 4 light years, we could get over to Proxima and Alpha Centauri, but I don't think there is anything else that we could reach. If we could reach a bit further out, we get a few more stars. And then something magical happens about the 7 to 8 light years of distance. Suddenly we can reach a fair number of stars, and many of them also have other stars, and we can spread across essentially most of the disk of the Milky Way. So this is called a percolation transition. It comes from studies of how liquids diffuse through powders. It started in geology when people were drilling oil wells, but it turns out in an astonishing amount of mathematics and physics, it's really wonderfully beautiful and you can apply it here to spreading through space. So there is a kind of distance limit. Can we move beyond that one? We can get most of a galaxy.
Wow. So eight light years is the gap that we need to be able to bridge.
There are of course going to be a few weird stars above and below the disk that we can't reach this way. Of course, if we're patient enough, stars move around and some move in and out of range. And then of course we have other galaxies. And again, we have big gaps. We're now talking about thousands to millions of light years. But if you can bridge that, we can get to the other ones in the local cluster. I calculated that if we can move some tens of millions of light years, then we can reach other galaxy clusters and basically take over the entire cosmic web. We can spread everywhere except maybe for a few places inside big galactic voids.
So what kind of time frames are we talking here in terms of settling even the local cluster of galaxies?
So I think it's pretty plausible that we can move at a fair fraction of light speed. And given that the local cluster of galaxies is about 2-3 million light years across, that would mean maybe between 4 and 6 million years if we move at half light speed. Which is a lot of time on our current human timescale, but astronomically nothing.
It's a blip. Yeah, it really, really is.
And the Milky Way, well, it's about 100,000 light years across if we count some of the outskirts. And again, at the half light speed, that's just 200,000 years. Even if we go much more slowly, it takes 1,000 years between each trip, and then you spend some hundreds of years on each settled planet and then build new spacecraft. Within some tens of millions of years, the disk of the Milky Way gets settled.
I mean, either way, it seems if we can get the technology to do it, then it's going to be no problem in terms of you don't need to worry about the universe's time limits, the stelliferous era ending and things like heat death and so on are so far away, like we're almost certainly going to be able to...
Almost, but not quite. So the problem is the local galactic cluster we can do in a jiffy. Getting over to the Virgo cluster, well, that's going to take a bit longer because now we're talking about hundreds of millions of light years. But it's still in the neighborhood. But suppose we start aiming at really remote galaxy clusters. So we send off our spacecraft as close to light speed as we can. But while it's going there, maybe 1 billion light years away, expansion happens. So it gets further and further away and the relative velocity decreases. Mm-hmm. So if you time it nicely, you end up going there with zero velocity. You start with light speed and you just park next to it.
Oh, you don't need to worry about deceleration or anything that.
No retro rockets or other complication. The problem is if you aim a little bit too far away, it runs away from you.
Right.
So there is an upper distance we can reach. It's about 4.9 gigaparsecs away. That is about 13 billion light years. So it's a lot. But that is a limit. We can see galaxies on the other side, but we can never ever touch.
Right. Well, and of course, because the ones that we're seeing are ones that we're looking 12, 13 billion light years into the past anyway. So presumably some of those are now already far beyond our reach.
Yeah,
ones that we can see.
Things get slightly complicated because the expansion of the universe has not been a constant thing. So it started out slowing down and then it began accelerating again. So there are complications about these distance measures which cause endless headache when you try to keep them straight, but still. But it means that we can only get a part of observable universe. There are parts of the universe that we will never ever affect, but we can still see them.
Right, of course. Yeah, because there's causally we can't have any impact, but we're still getting the information from the past.
Yeah.
So obviously this is getting pretty hypothetical. Is that a type 4 civilization?
So Kardashev's scheme started with the type 1 civilization that took all the energy on one planet, and then a type 2, which would be the Dyson Sphere one. A type 3 civilization would, in his scheme, be somebody using all the energy of all the stars in a galaxy. Mm-hmm. And we have actually had experimentalists looking for them. So there was the J-Hat survey looking at about 500,000 galaxies, trying to see is there something odd with the starlight coming from these galaxies, like if there was a lot of Dyson spheres around them. Sadly, none of them showed up. Some of them looked really weird, but didn't look like Dyson spheres. So there are probably no type 3 civilizations around us. We would probably have noticed. Mm-hmm. So maybe we are going to be the first. But you could imagine, of course, being even more ambitious. So you go out there and you settle all the galaxies you can settle. And now you're a type 4 civilization, but perhaps not for long, because that darn expansion means that your galaxy clusters get separated. So it becomes harder and harder to talk to the other parts of the civilization. And in about 300 to 400 billion years, basically they all get separated into their own little island universes.
And that actually raises an interesting question. Like, if a civilization becomes so large and the distances between them so vast, is it even still a civilization anymore if it can't communicate with itself?
Yeah. I think that communication is necessary to call it one civilization. You could still imagine that we decide that, okay, we're going to spread happy lives across the stars. The measure of utility is going to be happiness. So we spread a happy life to all the galaxies we can reach. And then they drift apart and you have all these little happy island universes. They can never talk to each other, but we kind of vaguely know that there are other happy guys out there. And this is really, really great. So that civilization might still be thinking that, yeah, we can't talk to others, but it works well. But you could imagine another value system saying, actually, a civilization needs to be communicated because it's a culture. It's supposed to think deep thoughts, create artifacts, do things together. In that case, you might only want to have a galactic supercluster that keeps together. The rest of the universe is kind of beside the point. Mm-hmm. Or you can be really ambitious and say, let's enlarge that cluster. So we are going to the outside of it and sending matter back to make it bigger so we can last longer.
Wait, you're talking about moving galaxies?
Yep.
How? How does that work?
It all starts with a lot of aluminium foil.
Okay.
Yes, really. So one way of moving...
The tin hat people were right, after all.
Yeah, this is
the
ultimate tinfoil hat. But it's used to send beams rather than deflect them.
Okay.
So what you do is you take a hemisphere of aluminium foil and put it around a star. A bit like the Dyson Sphere, but just on one side. And then you reflect the starlight in one direction. This is an exceedingly woozy rocket. Earlier we have been talking about actual rockets and we're using powerful lasers. Now we're using just starlight to try to move a star. The velocity changes.
Just photon pressure reflecting back, and that's slowly...
Yeah, slowly, and that is the trick, of course, because it's cheap. You can keep on doing this for a long time. And on average, if you keep it up for about 4 million years, you will have a close encounter with another star. And the stars will, of course, affect each other gravitationally and change orbits.
So it's a very, very slow but grand sheep herding.
Yes, indeed.
Of stars and galaxies towards where you want them to go.
Yeah.
Could you overcome expansion?
Well, that's the tricky part. So the stars, when you just move them with these so-called Skladov thrusters, are moving relatively slowly. But they have relative velocities in orbiting that are tens of kilometers per second. And now when they move faster, you can direct them to do other gravitational assists. So it's not just sheep herding, it might be the ultimate pinball. Because you can accelerate stars by having them move past a binary star and get some extra energy to speed it up. And you can put energy into the binary star by moving on the other side. Right. And you can have complicated free body interactions if you want to delay a bunch of stars because they're needed later. And you can also throw stars out of a galaxy with enormous speed by having them pass close to the central black hole. So we actually see this naturally happening. There are hypervelocity stars moving thousands of kilometers per second because they've been...
relative to the galactic center.
Yes, because we've been unlucky enough to almost fall into the black hole. Now, you could imagine using this as a really absurd rocket. You're sending stars past the black hole and expelling them at an enormous velocity. This could actually move the Milky Way 50 kilometers per second, enough to somewhat dodge the Andromeda galaxy, which is careening towards us and is going to hit us in a few billion years. The problem is that's going to use up most of the stars. I think the stars actually are the really valuable part. The dark matter we can't see any good use of it right now. Maybe a future generation would totally laugh at me saying this because they realize that dark matter is actually the valuable stuff and stars, who cares? But from a current perspective, if we think that stars are the stuff we care about, what we do is we turn the stars in the galaxy into hypervelocity stars and send them to the galaxy cluster we're building. So you essentially have galaxies depleted of stars, sending streams of stars against the expansion of the universe, slowing them down and then hopefully parking them well. I wouldn't want to be traffic control for this project.
Sounds hectic.
It's
Yeah.
hectic. It might, of course, it literally takes billions of years, so it might be hectic on that time scale. It might still be that kind of, it goes millions of years before each arrival. But still, you could build up much bigger galaxy clusters this way. So if your super civilization really wants to have a lot of mass energy that they can use in the very far future, as the stars go out and you need to turn that mass into actual energy to power yourself, this is probably the way to do it. And we can be pretty certain nobody else is doing it in the visible universe, because this would be very noticeable.
Something would be up in our telescopes. So if we got to that stage, that would make us a type 4.
Yeah.
Kardashev's, on the Kardashev scale. Is there a type 5? Is there anything beyond this?
So people have occasionally randomly suggested, so some say type 4 use all the energy in the universe, but we can't reach the rest of the universe.
Right.
Assuming, of course, that we're right about the acceleration expanding and the dark energy, which, given the fact that we have known about dark energy for just a few decades and are still very uncertain what it is, we might be really wrong about this. Maybe advanced civilizations just find a way of getting around that. And then they can get much more of a universe to do something with. You could, of course, imagine, what about other universes? Are there ways of sneaking over to them? I'm skeptical of that being possible, but again, who knows? Right. It's worth noticing that we have discovered quite a lot of things just the past 500 years after discovering the experimental method and science. And over the next 500 years, we can probably expect to discover quite a lot of equally earth-shattering things. And over the next 5 million years, which is still barely time to get to the local cluster of galaxies, science has probably advanced to really extreme levels. So maybe there are type 5 and 6 and 100 civilizations out there, but we can only analyze what we know about right now.
Right. So in terms of trying to quantify this, you mentioned before there is an upper limit to how many possible human lives could exist. What's your upper bound?
So my upper bound is somewhere slightly north of a Google future human lives.
So 10 to 100.
Yes.
Yeah.
And the way I'm arriving at this is that I'm looking at how much mass energy is there in the universe that we can access. And then assuming you convert that as efficiently as you can into computation, and assume that the people are running as computations, which is, of course, a few big ifs. Then you end up with on the order of about 10 to 100 future lives. Of course, it might be that they're very long lives, so then it's going to be fewer people, or it might be that a lot of them are very brief, or there might be just different ways of organizing. We're talking about a very advanced post-human civilization here. But the number is really large. That's the important part.
So if that's actually a feasible number that could be achieved, then it really speaks for the importance of what we do now, right? Because we are at this really interesting juncture where we could go extinct. I mean, a paper produced by the Future of Humanity Institute, I think it was 15, 20 years ago, put the estimate at somewhere around 20% of extinction by the end of 2100. I don't know, has that number been revised? Or?
Well, the number should be taken with an astronomically large grain of salt. But basically, the probability is big enough that it's worth worrying about. Even if it was just 1% risk, that's worse than a lot of things we actually do worry quite a bit about.
Right.
And it's worth noticing that this enormously large number, even if you say, yeah, right, I don't think you can upload people, then I will say, yeah, but we can still fill all these galaxies with organic people. And somebody might even say, yeah, right, I don't even believe you can build those nanomachines and those space probes. We have to settle for the solar system. And then I would say, well, 1 trillion people living for 5 billion years. That's an awful lot of people. Even if you go to the super modest thing, say we have 100 million people living simple and happy lives for, let's say, 800,000 years, which would mean that humanity survives 1 million years, which is kind of typical of a mammal. Still, 100 million times 800,000, that's an awful lot more people than exist today and have ever lived. The future, even at its most modest, is vastly bigger than our present. And I think actually the average future probably is towards the Google end of the side.
Right, and I mean, people, there's always a lot of discussion in terms of, how much do we value a future life that doesn't exist yet, but is likely to, compared to a life that is present right now. But I mean, everyone cares about even their unborn children, one generation away. Even if you have a sort of a scaling factor down, again, when you multiply this sort of value with the sheer number of possible lives that outweigh all the lives that we have today, the moral weight is enormous.
And many people, of course, don't do a calculation like this. They just feel. And it's interesting because future generations can sound very bloodless, but sometimes we have this experience that we don't want to break the chain. So a while ago, the Notre Dame Cathedral had a fire. And a lot of people were really emotionally taken by it. And it's interesting why. In some sense, that's just a dead, inanimate object. But of course, as a symbol for human aspiration, for culture, and indeed generations toiling away
Legacy,
at making it. Everybody realized, that is a great loss. We really need to restore it. And then, of course, we can argue about how to restore it. But we have similar projects going on all around us. When people are rearing the children, they actually hope their children will have children and so on. When people are writing papers, it's not just that it's going to be good for your career, but ideally that this is a valuable contribution to mankind. When you make art or anything, a lot of that assumes that there is a long-range future. And I think the risk of us going extinct here at the dawn of history, that's worth taking seriously. That's why we really need to be careful, figure out ways of making ourselves more resilient, avoiding the most stupid risks, spreading out maybe a bit so we reduce the risks a lot. So we have a chance of getting to these grand futures. Notice that I haven't been talking about what these super civilizations really do, because I have no clue.
Right.
I can't predict what the cultural values are going to be 50 years from now.
Maybe their goal is to just find out some ultimate truth of the universe and then they're done.
Yep.
Right?
Or it might be that at that point we realize, we've been going in the wrong direction all the time. Now we need to do these other things. It's very hard to predict future ideas because if we could, then we would already have them. So future societies might go off in all sorts of directions. We can outline using physics and a bit of this exploratory engineering I've been going on about, a bit of the limits. And that tells us a bit of the size they can be in. But where we actually choose to go, that's up to them. And of course, to some extent, up to us, because we're setting the start here.
Right, but it's arguably our moral duty to give them the opportunity to be able to make those decisions.
Yeah, we should aim at a kind of open-ended future. It would be horrible if we chained them down with what we think is really great. Because if we think back in history, what previous civilizations would have done, that's probably not very good by our standards. So.
One of my favorite phrases I ever read is just one simple sentence, and it is, love is that which enables choice. Right?
Yeah.
Because it's something that provides maximum optionality. And that's, at least certainly in my opinion, what we should be trying to do now is give as maximum runway as we can to our descendants in order to, we assume they're going to have better knowledge than us, better ability to use resource and reason and so on, to come to better moral decisions than us. So we just have to make sure that we give them the opportunity to do that, to exist in the first place.
Yeah, and once they exist, then they can really make the future grand.
Yeah, absolutely. So coming back to Earth a little bit, right now we've got visionaries like Elon Musk, I think Bezos, and some of the other sort of technologists who are looking into ways to advance space technology with the goal of getting us multiplanetary. What do you think is sort of the most important priority in terms of the steps we should be taking right now to do that? Is it the moon? Is it Mars?
I don't know really. I'm personally rather fond of mining asteroids, and the moon is nearby. But Mars, besides having awesome fantasy names for all the locations and being much more of a place than the moon and the asteroids, it also has practically all we know we need to build a civilization. It might be that on the asteroids you might need one type of asteroid to get some resource and another type for the other resources, so it might be slightly more awkward to mine. But the first thing we need is making it cheap to get to space so we can start experimenting. The reason we have been so bad at settling space has been partially that you can't do much experimentation if every kilogram you need to send to space could have been made out of gold for all we know, because it's so expensive. You need to make it cheap enough so people can start trying out things. Because the way with typical advanced technologies, we make some careful plan and then we try it. And then it doesn't work and we learn from that and fix it. The problem is, up until now, it has always been, it must work. So we spend an enormous amount of effort on design, which means that you can't really be very flexible. You can't actually figure things out. And to make a mining robot for an asteroid, you will need to have a device that can handle gravel getting into the gears. And if you need to plan for gravel in the gears on Earth, that's going to be a very slow development. We also need to have a good business plan for space. And this is where I think Bezos might have more ideas than Musk. Musk is kind of taking a lot of money he's earning on Earth to get to Mars. But it doesn't look like he's planning to earn a lot of money by being on Mars. While Bezos seems to be interested in the visions that you find in the 70s for Gerald O'Neill and others at NASA about actually building space habitats, building space industries. O'Neill pointed out that actually the planetary surface is probably the worst place you can have an industrial civilization. That's where you want your national park. That's where you want your people. You want to put the industry somewhere else. Of course, the problem of putting industry in space is you also need to send down products, etc. And for the foreseeable future, I think most space industry is going to supply space industry and space settlements on their own. So it's getting a good business model for space is really hard. So in terms of reducing existential risk, long term, settling many planets and ideally asteroids is really the way forward. Mm-hmm. Short term, it's probably not the most cost-effective way of reducing existential risk. We could probably make do with using that money for reducing pandemic risk and nuclear war risk.
Right.
But one of the cool things about space is that it can motivate useful research by the sheer cachet of space. If I were to suggest that let's make self-contained greenhouses, solar-powered, that using hydroponics can grow food in any environment, and I suggest that this is a great way of helping people in arid environments in developing countries, many people say, oh, that's lovely, Anders, but I wouldn't get any money. Saying this is to settle space. A lot of people get interested in, whoa, we should be doing that. And of course, the nice thing is, once we got that system that we can put on a space station or Mars, we can also put it in the Taklamakan desert. So I think actually quite a lot of these technologies are going to turn out to be super useful, because if you can actually settle Mars, then you can actually settle every corner of Earth too.
I went to a talk recently which discussed the viability of building a lunar base. Their argument was that it's the obvious stepping stone on the way to Mars, gets us a little bit out of the Earth's gravity well. And I heard a cost quoted of $2 billion to have a permanent lunar settlement, which was at least an order of magnitude less than what I expected it to be. What is your opinion on that? Do you think it would be suitable as a backup for existential risk, or is it too close?
I think it might be useful as a backup. If you could get it for $2 billion, I would be interested. I also have a suspicion.
Well, Will Marshall, if you know him, that's what he said.
It's a really cool possibility. I'm skeptical that you can do it that cheaply though. Right. And of course, mega projects generally tend to have cost overruns that are really big. And this might be the ultimate kind of mega project, which of course makes some of the earlier things I've been discussing about Dyson Spheres, etc., look very ominous in terms of cost overruns. But getting back to the moon, I think it's a useful testing case. Having a lunar base, you can put some stuff there. If you can make it self-sustaining, that's great. But it's not just that it needs to be self-sustaining. It needs to be able to actually expand using local resources without importing anything. If it can do that, now it actually is a bit of a safeguard against some existential risks.
And are there enough raw materials on the moon in terms of, are there metallic elements there and so on?
I don't see much problems with the metals. And we have found over the past decade and two that actually there is a fair bit of water, which is great. What worries me is nitrogen.
Right.
Because we're made out of a fair bit of nitrogen. Our plants are made out of it. Yeah, maybe you can replace the nitrogen in the atmosphere inside the base with some other inert gas. But still, nitrogen is relatively rare on the moon and in the inner solar system. Earth has a lot of it, but again, exporting that is tricky. You can find a lot of it in the outer solar system. After all, Titan got a lovely thick atmosphere with a lot of nitrogen, which I would love to bring over to habitats in the inner solar system. But that requires going rather far afield. Yes. So I think a lunar base would have to scrounge for nitrogen and a few other elements. It's going to be a fair bit of scarcity on the moon.
So if I gave you $1 trillion, what would be your plan of action?
For settling space? Well,
Yes.
first getting really cheap access to space. That's important. And then I would probably go trying. A lunar base is not a bad test case, but I want to mine asteroids. Carbonaceous chondrites contain a lot of raw material, including a fair bit of water and organics. And then, of course, you want some metal asteroids too. Then, of course, you want to be able to automate the production of solar panels, because once you have energy, you can recycle material quite well. So making solar panels in space might be another interesting adventure, because right now our standard solar panels are made out of pure silicon, and silicon is easy to get. But we purify it by reacting with hydrochloric acid, so you need to get chlorine, and that might be a bit scarce on some asteroids. It's actually surprisingly abundant on Mars. But you can make solar panels out of other things. You can, of course, use mirrors to heat something and run turbines. You can use pyrite, iron sulfide. It's a relatively bad solar collector. However, it's cheap, and at least, again, on Mars you find a lot of it, and I think you can find a lot of that in asteroids too. So we have a lot of options, and we probably need to explore many multiple options here, because we don't know what actually would work. The problem is that doing a top-down plan for how to do it is never going to work in reality. You need to have a lot of experimentation, and that means that it needs to be cheap enough to do the experiments, and also that you can survive making mistakes and flub it. But I think I could use up $1 trillion and probably get us into space. But we probably need better project managers and engineers than I am.
So you mentioned to me earlier that there are considerations in terms of the metabolism on a Mars base. Can you explain?
Well, in many ways, you can think of a Mars base as a living organism. It needs nutrients, it needs energy. It gets its energy presumably from solar panels, and it takes dirt and rocks on Mars and turns it into more Mars base. So the question is, can you actually make something that actually makes all its own parts? So there was a famous study in 1979 that NASA were thinking about a robotic lunar factory that we could build robotic lunar factories. And again, you get exponential growth and wait long enough and you cover the entire moon with factories that can make anything you want. That was still not getting all the details. And for example, there's a very important question of how you make microchips on the moon. And they actually cheated a little bit in their analysis on that. But if we think about what we know about Mars, I think we can sketch out that there is a metabolism for a Mars base. So James Yamona, who I met at the Aspen Institute for Physics, he has been doing some excellent work on this, and together we're now trying to extend this. So basically you want to take Martian dirt and atmosphere and turn it into metals to make machines. You want to turn it into something like concrete to build buildings. You want solar panels and microchips, and you want organics to make plastics. And it turns out that you can probably do this. The Martian atmosphere is thin and mostly carbon dioxide, and you can get water from ice in the soil. You can use your solar panel to turn the water into oxygen and hydrogen. And then you can react that with the carbon dioxide. You can make something called syngas, which is a mixture of carbon monoxide and hydrogen, which is very useful for reducing metal oxides into metals. So this is how you turn the Martian red sand into iron, for example. And you can use this in a lot of other things. You can, for example, turn that carbon in that syngas into methane by adding even more hydrogen. And then you can polymerize it. And now you can get hydrocarbons.
Right.
And you can quickly build up to all of organic chemistry, and now you have your plastics. You also want to get those chlorates, which are really bad for doing Martian agriculture, and get that chlorine out, put some hydrogen on it, and now you have got hydrochloric acid. Together with quartz, you can now distill pure silicon and make microchips and solar panels. You still need some dopants like arsenic or phosphorus, and they are relatively rare, but you don't need much of them. It actually looks like you can get most of these materials on Mars, given what we know about standard Martian dirt and atmosphere.
It's missing heavy elements though?
There have been enough volcanism in the past and probably enough water that are going to be some ore. So if you really want your lead or uranium, there is probably that, but that's going to require a lot more surveying and rovers looking around for it. So the problem might be that asteroids, while lovely a source of material, they're not that differentiated. When you have a planet like Earth and Mars, you tend to get material sorted somewhat into ores. in some sense, if you have enough energy, you don't care. You just take random material and extract. But that's a lot of heavy work. Normally you'd want to be effective about this. And also maybe you don't want to dig up the whole place. The reason you go to Mars might be that you want to actually have some pristine nature.
So one of my favourite papers produced by the Future of Humanity Institute is entitled Astronomical Waste, and it talks about, or tries to estimate, the number of, as you mentioned, there's this upper bound of perhaps a Google lives that could exist from now into the future. But every second that passes, good old entropy is taking free energy and dissipating it and basically taking away lives that could exist. Can you talk through a little bit about the process of how you came to this?
Well, you can make a rough estimation of how many lives there exist by looking at how far we can spread and then how long we can survive, and then make some assumption about how much resources different lives take. And the important thing is not what number you end up with, but that it's a big number. Typically 10 to the power of something with 2 digits. Mm-hmm. And we might quibble a lot about how I do these calculations, but typically that only moves it a few orders of magnitude. You still end up with another big number with 10 to the power of 2 digits. And then we have this problem. We're losing universe. Every year we lose about 7 galaxies that kind of fall off the edge of what we can reach. 7 galaxies.
That's a lot.
Yeah, each of them hundreds of billions of stars. That's kind of horrifying.
All that energy.
Yeah, and you kind of feel like we need to rush to build the rockets and go there. But the problem is, of course, that rush might actually risk everything. Because if we rush off to build the rockets and we accidentally destroy the world because we're doing stupid physics experiments or actually didn't watch our politicians with their nuclear buttons, etc., then we lose all of that. That's actually much worse than 7 galaxies per year. So the astronomical waste argument points out that the future is so big that much of the value lies in preventing threats to all of the future. That is existential risk here in the dawn of time. We're just out of the caves. We're kind of on our way to the rockets. But if we actually take too much risk now, that's much worse than losing some galaxies. Also, spending some time working on those rockets and make them faster might be quite valuable. Because if you travel too slowly, the expansion of the universe gives you a much smaller part of the universe. So it might be worthwhile to spend 1 million years perfecting your rockets and then go really fast than try to rush things.
Anders, thank you so much. This has certainly been one of the most fascinating conversations I can remember, possibly in my entire life. When is your book going to be out?
Well, hopefully before the technological singularity, because right now it's still expanding and I need to kind of start bringing it back and find a poor editor who can keep it short enough.
Well, it certainly is a big topic. If you guys want to find out more, do check out the links below. Certainly check out the Future of Humanity Institute's website. There's tons of brilliant stuff to read. Anders, it's been a pleasure. Thank you.
Thank you.
Well, folks, thank you so much for watching. If you enjoyed this and you want to see more things like it, then make sure you click that subscribe button below.